Ladies and gentlemen, welcome to Mr. Saucedo's YouTube videos. Today we're going to be going over how to predict products of different types of reactions. So follow along and make sure that if you have any questions you ask tomorrow. So we talked about synthesis reactions, and so the way that you can identify if something is a synthesis reaction is if you are mixing two different pure substances together. And so we're talking about, elements from the periodic table. So when you add two elements together, you always will be producing an ionic compound in this class. So it'll always be an ionic compound being manufactured. And so remember that whenever we write ionic compound formulas, the metal or cation goes first, and then the nonmetal or anion goes second. Remember to crisscross your charges so that you're actually making a real ionic compound and you're not just kind of making up your own formula for something. So let's start with the very first example. So solid calcium is mixed with fluorine gas. Alright, so we have solid calcium, so we're talking about our element here like this, and we have fluorine gas. Now remember, fluorine is a diatomic gas, so I have to put F2 like this. Alright, and when I am done with my reaction, I'm going to be making an ionic compound. So I have calcium fluoride, and I need to remember, what is my formula for calcium fluoride? So calcium is a +2, fluoride is a -1, okay, and so it would be CaF2. And so, by the way, here's another little fact for you. Whenever we're done making our ionic compound, that is going to be a solid. Alright, so it's going to be solid calcium fluoride. And that's the general pattern for each synthesis reaction. You're mixing two things together and you're producing an ionic compound. Remember to crisscross your charges and make sure that you're making an actual compound. Because otherwise, some people would just, on the other side put CaF. And CaF is not a real compound. It would be CaF2. Next up, we have solid sodium is mixed with nitrogen gas. Alright, so I have sodium, which is Na, and it is a solid. I have nitrogen gas, again a diatomic gas, so I have this. Alright, and then I'm going to be making sodium nitride because that's my ionic compound on the opposite side. So remember, I have to crisscross my charges. So what charge does sodium have? It has a plus charge. What charge does nitride have? It has a -3. So when I do my crisscross, I should get Na3N. And again, that is going to be a solid substance. And so just to go along with, sort of balancing our equations and everything, let's try to see if we can, balance this equation. So if I was trying to balance it, it would end up looking something probably like this. There we go. So we have 6 sodium, 1 nitrogen molecule, and then 2 sodium nitrides. Right, last but not least, we have solid zinc is mixed with chlorine gas. So again, I have zinc, and that is a solid. I have chlorine gas, so that's Cl2, and that is a gas. And then I'm going to be making zinc chloride. Alright, so the thing about zinc is it always has a +2, and chloride has a -1. So it would look like this, and it would again be a solid. And it looks like it's already balanced and everything else. So that's the way that you predict products for a synthesis reaction. Anytime you're mixing two pure substances together, you're going to be producing an ionic compound. And here's the other thing. It doesn't have to be a solid and a gas being mixed together. So it could be, other mixtures of things. It just so happened that these three were all solids and gases being mixed together. Next up, decomposition reactions. Well, in decomposition reactions, it's the exact opposite. So now you're breaking a compound into its pure elements. And again, my little hint here is please do not forget your diatomic elements when you're doing this. And so it's easy to kind of recognize a decomposition reaction because you only have one thing, and then it's going to be breaking into pieces. And so normally that's due to heat, like we said. So for our first example, we have solid disulfur pentoxide is heated and decomposes. Alright, so again, disulfur pentoxide. So I need to be able to write my formulas for things. So the disulfur looks like this, and then pentoxide looks like that, and it is solid, and it is being broken down. So when I do that, it breaks apart into its respective elements, its pure elements. So I have sulfur, which just looks like this, and that is a solid. And then I have oxygen, and so oxygen's a diatomic gas, and I have to remember that, and it would look like this. Again, I should probably balance all of these just to make sure that, I have this practiced enough. So I would put a 2 there, I would put a 5 here, and then I would put a 4 here. And that's how I would balance. Solid disulfur pentoxide is being heated and decomposes into its respective elements. All right, next up, water vapor is heated and decomposes. All right, so I've got water vapor, and that means it is a gas if it's vapor. Okay, it's heated and it decomposes, so it's going to decompose into its respective elements. And so remember, these are both diatomic, hydrogen and oxygen, like that. And again, I should probably represent this with a balanced equation. So I would put a 2 here, I would put a 2 here, and now it is balanced. Last but not least, liquid sulfur hexafluoride is heated and it decomposes. All right, so I have liquid sulfur hexafluoride. So sulfur, hexa means 6, so it would be SF6. It is a liquid according to this. It's being heated and it decomposes, so it's going to break apart into sulfur. Sulfur is a solid, if I look at my periodic table. And fluorine is a diatomic gas, so I need to make sure that I make that a diatomic molecule like this. So the only thing I need to do is balance this, and to balance it, all I have to do is put a 3 in front here, and now I have a balanced equation for liquid sulfur hexafluoride being heated and decomposing. All right, so again, when I'm dealing with decomposition reactions, I start with just one substance that I'm given, and I have to break it apart into its pure elements. Again, please make sure you don't forget your diatomic elements. And I just realized that's misspelled. I'll probably fix it on your handout though, so don't forget your diatomic elements. All right, combustion reactions, good old combustion reactions. The nice thing about combustion reactions is it's anytime you start with something with carbon in it and oxygen, and we know for a fact we're always going to end up with water and carbon dioxide because we're talking about complete combustion in all of these cases. So how are you supposed to actually, kind of understand if this is going to be combustion or not? Anytime we have, again, carbon-containing compounds and oxygen being mixed, they're going to be ignited by, sort of a flame or something, and that's going to kind of be your key. So when you see ignite, that's going to be kind of like, oh, that must be combustion. Let's start balancing these and writing out the chemical equations, though, because remember, we know what we're going to end up with for combustion reactions, so it's not going to be too bad. It's going to be C3H8, and that is a liquid, and oxygen gas, so again, I have to make sure I write that down as O2, and remember, you always make CO2 gas and water. And here's the thing about the water that you make. It is water vapor. It doesn't necessarily have to be liquid water. To be honest with you, it doesn't really matter if you put liquid water or, sort of water vapor, so gaseous water. Both would be okay representations. Now I should probably try to balance this. All right, so let's balance this equation. So I will put a 3 here, and then I would put a 4 here. And then I'd have to add up all of my oxygens, so 8 and 6, and so I guess I would probably have a 5 here. And that would be my balanced equation for liquid C3H8 and oxygen igniting to form carbon dioxide and water. All right, next up, I have liquid C4H8. So again, I'd write that down, C4H8. It is a liquid. And oxygen, again, that is diatomic, and it's going to be igniting, so that means that I'm going to be making CO2 gas and H2O, and again, it doesn't matter whether I put liquid or gas there for water. Okay, so I guess all I really need to do then is balance this equation. So let's follow along with that. All right, so I would have a 4 here, and I would have a 4 here, then I just need to make sure I add up all of my stuff. Okay, so it looks like that would be a 6 for oxygen then. 8, 9, 10, yeah, all right, so that should be a nice balanced equation for liquid C4H8. reacting with oxygen and igniting to form CO2 and H2O. All right, last one. So I've got liquid now C6H12, and I've got myself some oxygen gas igniting. So that means I'm going to be making CO2 and water again. I've got CO2, I've got my water, and now all I really need to do is balance my equation. All right, so when I balance this, I should put a 6 here, and a 6 here. That should add up, and then I need to worry about my oxygens, and so that'd be 18, so that'd be a 9 here for my balanced equation. All right, so that's how we deal with combustion reactions. Anytime you see a carbon-based compound and you're mixing it with water, when you ignite them together, you will get a nice, complete combustion. So that means we're making water and carbon dioxide. Now these last two, single displacement and double displacement, they're going to look a little bit more complicated, but they're pretty simple once you actually get into the practice of just sort of switching things around a bit. Okay? So we'll deal with single displacement first. In single displacement, you're going to have a metal, and it's going to be replacing the cation in the other compound. And so my hint there is to keep your charges the same, unless it's an ion that only has one type of charge, like we know zinc is always a +2 or something like that, because it will make it a lot easier if we try to balance these, if you keep your charge the same. Okay? So how are we supposed to identify that? Single displacement and double displacement reactions always look more complicated. So when you have a lot more description, it's probably going to be either single or double displacement as a result. Okay? So it says solid, solid. And again, I guess I have to probably fix that on your slide. So it should say solid sodium. There we go. So solid sodium is mixed with aqueous magnesium chloride. All right, so let's write out. Solid sodium is Na like this. Aqueous magnesium chloride looks like this. AQ. All right. So what am I doing? Well, I'm going to be replacing one metal with another metal. So I'm going to take my sodium and I'm going to put it over where magnesium is. And it says, remember, try to keep your charges the same unless it's an ion that has only one type of charge. So here's the thing, magnesium's a 2+, sodium is always a +1. So when I do my replacement, I got to make sure that, everything is nice and taken care of on the opposite side. So I'm going to be making sodium chloride, which is just NaCl, okay? And we're not going to be dealing with any state changes here. So we're not going to put down, solid, liquid, or gases on the opposite side when we're dealing with single displacement reactions. Okay, so for the time being, that's kind of the rule that we're going to be using. So for single displacement reactions and double displacement reactions, don't worry about whether it would be a solid on the opposite side or aqueous or a gas or whatever, because there are special rules for that, and we won't be talking about them until, a couple of days from now. So NaCl is what I'm going to be making, and then I'm going to have my metal by itself. So I've got that, and then I've got my Mg on the opposite side. Magnesium has now been pushed out of the way by sodium, so sodium makes a compound, and now I just have magnesium all by itself. That's what single displacement reactions do. So if I want to balance this, which I easily could, I would just make sure everything balances on both sides. So I would put a 2 here, so I have the same amount of chlorides on both sides, and then I would put a 2 in front of my sodium to make sure that my sodiums add up, and that should be done. So that's the way single displacement reactions work. Let's try another example. Solid iron is mixed with aqueous nickel 2 carbonate. All right, so again, I have a metal by itself. I've got iron. It's a solid, and I'm mixing it with aqueous nickel 2 carbonate. So I need to remember nickel 2 carbonate looks like this. It is aqueous. And so what am I going to be making? Well, I'm going to replace iron with nickel. So nickel and iron are switching spots. So I'm going to be making iron carbonate, and so that's why that little underlined part, which now I'm going to put in a box, keep your charges the same, kind of comes in handy with transition metals. So since nickel was a +2 in my compound that I started with, I'm going to make iron a +2 as well. So I'm going to make iron 2 carbonate, so just FeCO3, Again, don't worry about solid, liquid, or gases on the product side for these. And then I would have nickel all by itself as a result. And so I'm done. I don't need to balance this one. It's already balanced in the process of me keeping the charges the same. So that's kind of nice. And that's the way the second example for single displacement reaction would work. All right, next, solid aluminum is mixed with aqueous zinc acetate. So again, I've got solid aluminum right here, and I've got zinc acetate. All right, so I need to make sure I write that down correctly. So that's parentheses, C2H3O2, like that, and it is aqueous. So in case you forgot, zinc acetate, zinc is a +2, acetate is a -1, so we've got zinc, Zn, and then in parentheses, C2H3O2, and there would be 2 of them to keep that nice and electrically neutral. Okay, so what am I doing? Again, aluminum and zinc are replacing each other. Aluminum always has a +3 though, and zinc has a +2. So I can't really keep my charges the same there because my ion it won't work out that way. All right, so I hope I have enough space. If I don't, I might need to clear the slide. So I would have aluminum acetate. Oh, I'm not going to have enough room, but it's okay. Aluminum, Al, acetate, C2H3O2, and then I would have a 3, since aluminum has a +3. And I would have zinc all by itself then. So plus Zn plus zinc. Now I probably should balance that, because that's going to be something kind of important to do. So the key thing here is my acetates do not look anything alike. So I would put a 3 here, and then I would have to put a 2 here. And by doing that, I would put a 2 in front of my aluminum, I would put a 3 in front of my zinc, and now that would be balanced. So the thing about single displacement reactions is literally you're just replacing one metal with another, but just like in all of these, you have to be able to make realistic compounds on the opposite side. So remembering your charges and how to crisscross them and what is a real compound and what would be a fake formula is extremely important, especially in single displacement reactions. Last but not least, double displacement reactions, the ones that are probably the most difficult to write out. All right? So both cations and anions switch spots. Make sure you recross all your charges on your product side so you write real compound formulas. So again, you got to make sure you're writing real formulas. You can't just sort of like, stick one thing with another and expect it to be real, because sometimes it will be, other times it won't. So you'll need to make sure you crisscross charges. So I've got aqueous lead nitrate is mixed with aqueous lithium hydroxide. So again, I have lead 2 nitrate. So I've got lead, and then I've got nitrate like this, and it is aqueous. And then I have aqueous lithium hydroxide. Just like I mentioned with single displacement reactions, you don't need to worry about the states of matter on the opposite side. So what's happening? I take my metal, and I'm going to pair it up with my anion on the opposite side. So Pb is going to get paired up with OH. All right? And then on the inside here, I'm going to pair up my, metal and my anion again, like this. So that's what swapping ions, when we're talking about double displacement reactions, looks like. And again, just like in a single displacement reaction, if I keep my charges the same on both sides, if possible, it'll make, sort of my life a lot easier as a result. So right now, I'm going to be pairing up my lead 2 ion and my hydroxide ion. So lead 2 hydroxide looks like this. Lithium nitrate looks like this. Again, that's what I end up with. So I end up with lead 2 hydroxide and lithium nitrate. And so again, if I want to balance any of these things out, all right, I'd put a 2 here, I'd put a 2 here, and now I think I'm balanced. Okay? So that's double displacement reactions. Next up, aqueous barium chloride. All right, so I've got barium, I've got chloride is a -1, and barium's a +2. It is aqueous, like we just said, and I'm mixing it with aqueous sodium phosphate. So sodium is a +1, phosphate is a -3, and again it's aqueous. So just like before, I'm going to take my metal from one compound and pair it up with the anion. So I'll just do this. So those are going to get paired up. I take my metal from the other compound and pair it up with the anion from the other one. So I'm going to pair up these guys. Remember, if I keep my charges the same, if possible, I can, but in some cases, like sodium only has a +1, barium only has a +2, so I need to make sure that I'm making, again, real compounds. I can't just make them up. So I'm making barium phosphate. Okay, that's going to look a little bit complicated. So barium, like this, okay, it would be 3 since I have phosphate, and no, phosphate's a -3. Phosphate, though, since it's a -3 and barium's a +2, this is the way barium phosphate's formula would look. And then the nice thing is I have NaCl, so I have sodium chloride that I'm making as well. So I have NaCl. Again, when we're trying to balance these, I want to make sure that I have everything accurate on all sides. So I need to make sure that I have everything balanced, like I said, and so I would put a 3 here in front of barium to make sure that my bariums are all nice and taken care of. I'd put a 2 in front of here to make sure my phosphates are all taken care of, and then I would have 6 in front of my sodium chloride to make sure that everything's balanced there. All right, and so that's how I balance letter B. Last example, so I've got calcium chloride is mixed with potassium carbonate, and again, they're all aqueous. So I have calcium chloride, again, making sure I know my formulas and how to do all of that, and then aqueous potassium carbonate. All right, so potassium's a +1, carbonate is a -2, so it would look like this. And again, on the opposite side, all I'm going to be doing is I take my metal and I pair it up with an anion, so Ca gets with CO3, and then I take my other one, so I have K, and I'm pairing that up with Cl on the inside like this. And so when I do that, I make calcium carbonate. Calcium always has a +2. Carbonate always has a -2, so that's already taken care of. And then I have K, which is a +1, and Cl, which is a -1, so they're already nice and taken care of as well. All right, so again, if I want to balance this, I need to make sure that everything's the same on all sides. So all I would need to do is put a 2 here, and now I would have a balanced reaction for aqueous calcium chloride mixing with aqueous potassium carbonate. All right, so as my final hint for double displacement reactions, always, always, always make sure that when you pair things up, you pair them up as I did. Okay, so metal goes with the anion on the opposite side. Metal goes with the anion on the opposite side. That was the pattern, and that will never, ever, 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 ever change. Also, make sure that you are writing real compounds on both sides. That means that you have to keep track of your charges and re-crisscross them when you have to. All right, so that's absolutely everything for predicting the products of reactions. If you have questions, bring them tomorrow.